Swayam Prabha. Digital India. Educated India.
So let me remind you what I did, okay? I gave you the algorithm for how to generate the lower and upper bounds on the innermost dimension, okay? So I had a polyhedron where I had these n indices, and they were all, I had some expressions that were, there were linear inequalities that were that defined that polyhedron. And I wanted to generate a loop program that visited all those points in the polyhedron. I found the way to generate the innermost loop, which is the lower bounds on the nth, the innermost index, as some lower bound expressions involving all the n-1 indices, and also some upper bound expressions on the same n-1 indices. Okay? Now what do? I have to eliminate the index that I have for which I have already generated the bounds. So I basically have a polyhedron in the outer n-1 dimension, z1 to zn-1. Okay? And I'm going to construct that polyhedron. It is the polyhedron that satisfies by transitivity that any lower bound expression is less than or equal to any upper bound expression. If I just eliminate the Zn by transitivity, what do I get? Okay. For each pair UILJ, an upper bound, lower bound, you introduce a new inequality. UI expression is greater than or equal to LJ expression. Okay. So pairwise, you pair all the lower bound expressions with all the upper bound expressions and get get inequalities that involve only the n-1 indices. Once you have constructed this, you recurse and find the bounds on the innermost dimension of that. Once you've done that, eliminate z sub n-1, and you will have you have a polyhedron that defines a set of indices, the bounds on the inequalities that I1 to in-2 must satisfy, and so on. You work your way inside out, and at each step you do this that I have in the previous slide, construct the loop, and then eliminate Zn and get pairwise all the inequalities involving some lower bound expression, some upper bound expression. And you're done. Okay? So why does this work? Okay? The original polyhedron can be viewed as the set of points that satisfy all these, that satisfy these inequalities intersected with the set of points in the n-1 dimensions with no bounds on Zn that involve these inequalities. Okay? We are still always talking about the set of points that are in, for the correctness argument, you're still talking about points in this n-dimensional space. All you're saying is that on the innermost dimension, there are no constraints, so it can be arbitrarily large, no lower bound, no upper bound, because that has already been generated from the previous slide. Okay? So In is the intersection of I sub n-1 and the bounds on the nth loop. Okay? So I did an example on the doc cam, but I don't have that right now. Okay? I have to talk to you and explain to you one final thing. Okay? You now have a loop that visits this new space T and P. Okay? But you don't know what the loop body is. Okay? And once again, this this part of the problem uses the inverse. Okay, and I'm going to show this to you again pictorially. Okay, you have a set of points. Okay, that is this new polyhedron. From that, you have generated a set of loops that visit I and P, or T and P, in the appropriate order, so that I will be visiting all of these points from left to right and column by column within each, column by column from left to right, right? And within each column, I'll go top to bottom. Okay? What is the statement that must be executed at this point TP? I'll give you a very simple rule. Okay. Can you see my cursor? Are you able to see my cursor?
No.
Okay, so think of this as the point TP. It is the image of some point ij in my original rectangle, right? And the statement that must be executed is exactly the statement that was executed at the point ij that was mapped to this point TP. So what I'm going to do is I am simply going to, in my loop, I am going to define two new local variables, okay, called I and j, and I equals the inverse mapping applied to TP, and j equals the inverse, the second component of the inverse mapping applied to TP. Okay, and then I'm going to verbatim copy the old loop body. There are sort of more sophisticated ways of doing this, but if you are doing this as an exercise, this is the simplest way. Okay, so here's what I have. I had the T loop for T equals 1 to n plus m minus 3 T plus plus. I have my parallel pragma, and then I have the lower bounds on the bounds on P, the loop on P that I have generated. I say I equals P, J equals T minus P plus 1, and I insert verbatim the old loop body unchanged. We can do this provided the new index names that we chose are distinct from the old one. And that's what I did. I chose T and P rather than reusing the names I and J. Okay? All right. Let's try. Can you remind me how we're doing for time? I don't see the 10 more minutes, right? So let me ask you the following. I have this new program where, remember, I'm going to work on example 2, and the example 2 had a new additional dependence. Ij also depended on its northeast neighbor because the northeast neighbor had to be executed before the point ij, because it was a consumer of the value that was going to be overwritten by the iteration ij. Right? So can you think of a schedule for this program? This is not an easy question, so think hard about it. And you can still think of this idea of looking at this as a graph, finding out the sinks. And so I gave you the first sink. After you remove this sink, what else can be done? This graph has a sink, which is the topmost, the northwest corner of the graph. If you remove that node, so that is the one that has to be done at the first time step. After that is done, the residual graph is the one in which we have removed that sink node and all edges incident on it. In that residual graph, is there a sink? Or are there multiple sinks?
One sink, 0,1.
There are two.
Which two? 0,1 I see is a sink, and what else?
1,0 also.
1,0 has an outgoing edge to 0,1. That red edge out of 1,0.
Yeah.
Okay, so ignore the color. The red is simply because it was a memory-based dependence. It was not a true dependence, but that is a dependence. Okay, so therefore 1, 0 is not a sink. After the first sink is removed, there is only one sink, and which is 0, 1. Right? Everyone agrees?
Yes.
Okay, let's remove that sink and all edges incident on that. Now what is the sink?
0,
So you remove 0, 0, you remove 0, 1.
0, 2 becomes the sink.
0, 2 is a sink.
And 1
And
comma, it's 2 comma 1.
1,
2 comma
0
1.
has now become a
2
sink.
comma 1.
Sorry?
It's okay. It's 1 comma
The vertical axis is the
yeah, 1 comma 0.
y-axis. The origin is 0, 0. Top left is 0,
Yeah.
0 in the
Yeah, 1
convention
comma
that
0.
we have just. So 1, 0 and 0, 2.
Yes.
There are two sinks. If there are two sinks, then there is parallelism. Both of them can be executed in parallel. Very nice. What else? After you remove those, yes? Hey, you have another family of straight lines, which can be interpreted as time steps. Notice that for every line, the edges coming out of it are strictly backwards to a strictly preceding time step. Okay? Isn't that nice? Yes? So, I gave you sort of some intuitive ideas on how to find such a schedule. But of course, like I said, there is a huge body of work that describes how to find the schedule. Now, what do we do? Well, what is this mapping? Okay, so the time step is 2 times I plus j. If you increment I, that means you go from one row to the next row, you're crossing 2 time steps. Right? 2 times I plus j, ignore the constant, is my schedule function. Another way of looking at it is that look at my timelines, these bold red lines. Okay, what is the normal vector to it? 2, 1. 2i plus j is therefore the schedule. That gives you the first row of this transformation T that we were talking about. What about the second row? Because remember, it has to be a 2 by 2. I have a 2-dimensional space. I'm going to get a 2-dimensional space. Okay. Well, what if I take every row and shift it to the right by 2 more than the previous row? In other words, all the points in a row remain on that row. Okay? That means the P index is the same as the old I index. So I'm sort of giving you all these visual intuition on imagining this, but here is my mapping. Ij goes to Pt, where P is I, and time step is 2i plus j minus 2. The inverse of this transformation, we can figure it out. The transformed iteration space, we can apply exactly that same rule. I took the constraints, I took the inequalities, I replaced wherever there was I by this expression here. Wherever there was j, I replaced it by this expression. I can rewrite this, and now I write the new loop. Okay? And now I have some situation where I'm dividing by 2 because I have 2 times t. Okay? When such a division by 2 appears on a lower bound, I have to take the ceiling. When that expression appears on an upper bound, I have to take the floor function. But other than that, this is just applying the same old rules again. Okay. I think what I'm going to do, because we are close to the end of time, I'm going to stop. And there are a few slides. I will, I'll be happy to post the slides or send them to Rama. You can study them. But I think it's more important that, if you have questions, we clarify the questions. That is more important.